Welcome to today's discussion. We'll be exploring a research paper titled Moonshine, Speech Recognition for Live Transcription and Voice Commands. This paper introduces a new family of speech recognition models designed for real-time applications on resource-constrained devices. What are the key challenges in developing speech recognition for such devices?
The primary challenge is minimizing latency, the delay between speech and the appearance of transcribed text without sacrificing accuracy. Existing models, even smaller ones, often have significant latency, even for short audio clips, due to fixed-length processing. This makes them unsuitable for applications requiring a smooth, responsive user experience, like live captioning.
So the paper addresses this latency issue. How does Moonshine differ from existing models like OpenAI's Whisper?
Moonshine avoids the fixed-length processing of Whisper. Whisper processes audio in 30-second chunks, even if the audio is shorter, leading to unnecessary computation. Moonshine scales its processing proportionally to the audio length, eliminating zero padding and significantly reducing computation for shorter clips.
That's a significant improvement in efficiency. What architectural choices enable this variable length processing?
Moonshine uses an encoder-decoder transformer architecture, but instead of traditional absolute position embeddings, it employs rotary position embeddings, ROPE. This allows the model to handle variable length sequences effectively. The encoder's processing time is directly related to the audio length, unlike Whisper.
The paper mentions a substantial speedup compared to Whisper. Can you elaborate on the performance gains?
Moonshine Tiny, the smallest Moonshine model, achieves a 5x reduction in compute requirements compared to Whisper Tiny.in for a 10-second audio segment, without any increase in word error rate, WER. This is a substantial improvement for resource-constrained devices.
The paper also discusses the dataset used for training Moonshine. What makes this dataset unique?
Moonshine's training data comprises around 200,000 hours of speech, combining publicly available datasets with a large internally collected dataset. A key aspect of the internal data collection involved pre-processing noisy and unlabeled data using techniques like filtering based on Levenshtein distance and average log probability from Whisper Large v3.
The paper highlights the importance of handling variable length sequences. What were the results of experimenting with different position embedding strategies on Whisper?
Attempts to adapt Whisper to variable length sequences by simply truncating the position embeddings resulted in significantly higher WERs. Using only the prefix led to a WER of 107.38%, while using the suffix resulted in 18.45%, both far exceeding the baseline WER of 5.21% with zero padding. This demonstrated the need for a model specifically trained for variable length sequences.
The paper shows a comparison of WER across different datasets. Were there any significant differences in performance?
Moonshine generally outperforms Whisper on most datasets, achieving comparable or better WER. However, it performed less well on the Earnings 22 dataset, which contains many very short utterances. This suggests a need for more training data representing such short segments.
The paper also evaluates the performance across different audio lengths. What were the findings?
Moonshine maintains superior WER compared to Whisper, especially for shorter audio segments. For longer segments, both models show increased WER, likely due to limitations in contextual information and potential hallucinations.
The robustness of the models to noise and varying input signal levels was also tested. What were the results?
Moonshine showed comparable robustness to Whisper in the presence of additive noise. Regarding input signal level, Moonshine maintained superior WER across most of the tested range, only degrading significantly at very low signal levels.
The paper mentions some limitations. What are the areas for future improvement?
Further research could explore different model architectures and optimizers. Improving generalization to shorter audio segments, particularly those found in datasets like Earnings 22, is another key area. This could involve collecting more representative data or exploring training techniques to improve contextual information.
The paper concludes by highlighting the potential of Moonshine for real-time ASR applications. What are some of the potential applications?
Moonshine's low latency and efficiency make it well suited for live transcription, accessibility tools for the hearing impaired, and voice command processing in smart devices and wearables. Its ability to run efficiently on low-cost hardware opens up new possibilities for these applications.
The paper acknowledges the use of the Cashless Transformers library. How significant was this contribution to the development of Moonshine?
The Akashics Transformers library provided a solid foundation for the Moonshine training code, simplifying the development process and enabling efficient training on a GPU cluster.
This has been a very informative discussion on the Moonshine speech recognition model. Thank you for sharing your expertise.